To learn the general approach to conservation of energy calculations, we're going to look at this question, which is very similar to the skateboarder, which we saw in the FET simulation in the last video. And this question comes from an old exam. The miners working in a salt mine use smooth wooden slides to move quickly from one level to another. And this is very like the skateboarder. They're starting at the top of the ramp and finishing at the bottom of the ramp. So let's look at how we can apply a general approach to solving these questions. So the general approach is going to be to use a suitable equation to calculate the energy in one store at the start. Then we apply the idea of conservation of energy to say that at the end, that energy has shifted into a new store, and it will be exactly the same amount of energy as we calculated at the beginning. And then finally, knowing the energy in the different store, we can hopefully calculate something interesting. Exactly how this works will hopefully become clearer as we work through this example. So another way of saying it is we'd use one equation to calculate the energy at the start point, which might give us, for example, that it's 200 joules. And then we realise at the end point that 200 joules has now transferred into a different store. So we now know how much energy is in that different store because of conservation of energy, and we can use a different energy equation with the energy equal to the 200 joules to calculate something interesting. At this point, we should make sure we can remember some of the key equations. Can you pause the video and see if you can remember the equation for work done, elastic potential energy, gravitational potential energy, and kinetic energy? I should say this one you can look up from the equation sheet you're given in the exam, but you might be able to remember it without that. Okay, hopefully you have remembered. Work done is force times distance moved in the direction of the force. Elastic potential energy is a half times the spring constant times the extension squared. Gravitational potential energy is mass times gravitational field strength times height. And kinetic energy is a half times mass times speed squared. Might be a good idea to make a note of those equations near the top of your notes so that you've got them to easily refer to. It might also be worth realizing that sometimes in questions you might need to remember related equations like the Hooke's law, force equals spring constant times extension, because you might use this to work out K before using it in the elastic potential energy equation. Back to our example. In our example, a typical question might be calculate the speed of the miner at the bottom of the ramp. But in order to do that, we need to start by thinking, what equation could we use to calculate the energy that they have at the start point when they're at the top of the ramp? So think about which energy store is filled there, and so which equation might they be able to use to calculate the energy at this start point? Hopefully you have realized that the equation that they can use is the gravitational potential energy one. And that is because they are high up, so there would be lots of energy in their gravitational potential store. So we're given a bit of data in this question, and so let's work out the gravitational potential energy at the start. So this will be gravitational potential energy is their mass, which is 80, times gravitational field strength, which we're given as 9.8 newtons per kilogram, times the height, which is 15, which if we work out on a calculator comes out at 11,760 joules. The next crucial step is realizing at the end all that 11,760 joules has transferred into a different energy store, which is going to have the 11,760 joules in it. And hopefully, by thinking back to the skateboarder, you can realise that this energy store that it's transferred into is kinetic energy. So we can deduce that the kinetic energy at the end, when they're at the bottom of the slide, is equal to 11,760 joules, which is exactly what the energy was as gravitational potential energy at the start. Now comes our third step, where we can use the different energy equation to calculate something interesting, which in this case is we can now use the kinetic energy equation, or equals a half mv squared, to calculate the speed of the miner at the bottom of the ramp. So we will substitute in the numbers, which is 11,760 for the kinetic energy is equal to a half times 80 times v squared, which will simplify to 11,760 equals 40 times v squared. Therefore, v squared equals 11,760 divided by 40, which gives us v squared equals 294, which will therefore give us that v is equal to the square root of 294, which will be 17.1 meters per second, rounding to a sensible 3 significant figures. So in summary, what we did was we worked out the energy at the start and the gravitational potential energy and got that as a number, which in this case was 11,760. We then said by the time they get to the end point, all of this energy will be in kinetic energy, and therefore we can say the kinetic energy at the end point is 11,760. And then we can use the kinetic energy equation to calculate our interesting thing, which in this case was the speed at the bottom of the ramp.